So this is still chapter 15. What we're going to talk about is something called K, and finding out which way does the reaction tend to go. Does it go more forward or does it go reverse? And this is going to be how we're going to figure that out. So it's going to be a capital K that we're going to be talking about. So generically, this is usually how they show an equilibrium reaction. And the lowercase letters are, of course, the balancing, and the uppercase letters are the formula. So this K that we're talking about is sometimes called KEQ. It's sometimes, I'll explain that a little later, but it's always going to be the products over the reactants. So we are going to take this generic form here, and we're going to use brackets to denote concentration. So we're going to put the products on the top, and we're going to take it to the power of whatever the stoichiometry is, okay? I realize that this is a multiplication. Sometimes students think it's adding, but it's multiplication. And then we are taking the reactants and putting them on the bottom as well, to the power of whatever they are, okay? So again, the brackets mean molarity. We talked a little bit about that when we were doing kinetics, so that's going to be exactly the same. Now, what's interesting about this particular K are there no units for this. So we did have like a small k for kinetics, and it did have a unit. These, I don't know why you couldn't do it, but we do not have units for this. We're going to have different Ks as we go along. Ka, Kb are going to be when we get to acid-base chemistry. We're going to talk at the end of this lecture about something called KSP. So Ks in general are always going to be looked at as products of a reactant. You're just going to see letters on the bottom that are going to mean something different for the situation that you're at. So the first thing, what this is called the the equilibrium expression. So if I give you a real balanced chemical equation, can you write the equilibrium expression? So all you got to do is put K is equal to the product, the formula, in the brackets. And then the H2 on the bottom is going to be squared because there is a 2 in front of it. So this is what we call an equilibrium expression. Now please note that everything is a gas in this equilibrium, and we're going to come back to if it's not a gas, what do we have to do? So the second part, once you have found the equilibrium expression, you might be given concentration values at equilibrium. So I want you to think back to when we did the ice chart. So these numbers at equilibrium, these are the numbers that we're going to use for our K, okay? So these are the concentrations of all the species at equilibrium. So I'm going to take my product, which is 1.56 molarity, and then my CO is 1.03. My H2 is 0.322 molarity, and I have to square that on the bottom. And again, molarity doesn't really matter because there are no units for this. So when you plug it into your calculator, you get a number about 14.6. And again, no units, so I guess that's good. So what does that tell us about the equilibrium? So again, it is always products over reactants, products over reactants. So if this number is a big number, that means you have more products. So this is generally how we break down the K. Is the K greater than 1 or less than 1? If it's greater than 1, we say products are favored, meaning it goes more towards the right-hand side than the left-hand side. If K is less than 1, that would mean you have more reactants on the bottom. So think of how you divide those numbers. So that means the reactants are favored. So really, it's going to be pointing more towards the left than the right. And what if you happen to have K equal to 1? Well, that kind of means that your amount of products is equal to the amount of the reactants. It doesn't happen very often because, again, you have to be exactly the same, and it has to account for anything that's squared or anything like that. So really what we're looking at is it greater than 1? What does that mean for the equilibrium? So since this is 14.6, we're going to say products are favored. So when we look at this reaction, we're going to probably have more products than we do reactants. All right, so those were all gases. Well, what do we do with an equilibrium that have solids or liquids in them? Okay, so this is calcium carbonate plus some acid produces calcium ions, water, and carbon dioxide. So what I want you to think about is solids and liquids. Okay, do they have concentration? Okay, can you have a concentration with those? You can't. Okay, you have density though. Okay, you do have density of solids and liquids because that is going to be intrinsically part of what makes something water is its density, or calcium carbonate is going to be how those things are arranged. So the only things that we have molarity for are going to be gases and aqueous solutions. Okay, so that means with K's, okay, write this down. You never include solids or liquids in the expression. Okay, so you never include solids or liquids in an equilibrium expression. So if I were to write the K for this reaction, okay, I would just have to put calcium ions and CO2, and then on the bottom, H plus squared. That would be my proper K for this equilibrium. Now, if I am talking about concentration, this is sometimes called Kc, okay? Sometimes it's just K, sometimes you will see KEQ, all kind of means the same thing. So if you don't see anything written there, it's going to be concentration, but you sometimes see Kc. But you're also going to have something called Kp, and this is going to be for gases. This is going to be for gases. So Kp is going to be exactly the same as Kc, except you're going to be looking at pressure. Okay, so what you're going to see are things in parentheses, and it's going to be pressure. You're going to do exactly the same thing if you have two in front of it. You're going to square it so far, same as before. And so this could be in atmospheres, this could be torrs, millimeters of mercury, just as long as you have the same pressure unit. And this is the tricky part. I will specify what unit you should use because you don't really get any information from a K. So for this particular reaction, okay, the only gas we have is the CO2. So my Kp would actually just be the pressure of CO2. So that looks different from the Kc. Now, if I went back up to this equation, this would be exactly the same. I would just take the brackets away and put parentheses and put pressure instead. So it's again exactly the same setup, exactly the same setup. So flip it over to the next page. I'm going to work this problem here. If I have my Haber process of making ammonia, if I have 200 atmospheres of nitrogen is mixed with 100 atmospheres of hydrogen at 250 degrees Celsius, find the Kp at that temperature if the final pressure is 239. So what we could do with this is, of course, we could do a ice chart essentially as pressure units. So we kind of did this before with some other problems we've done. So we have 200 atmospheres for the nitrogen, 100 for the hydrogen, and I have no ammonia to begin with. Okay. So then change minus x minus 3x plus 2x. And I know at the end of this reaction, this is going to be my concentrations at equilibrium or at that particular pressure. So I know that if I add all of these up, I will get a total pressure of 239. So I'm going to take 200 minus x plus 100 minus 3x plus 2x is equal to 239 atmospheres. So again, I got negative 4x, I got a 2x, so x comes out to be about 30.5 atmospheres. So I want to find the Kp. So if I find the Kp, I need to find the individual pressures for each one of these. So nitrogen is going to be, again, 200 minus the 30.5 is going to be about 169.5 atmospheres. The hydrogen is going to be 100 minus 3x, so 3 times that number. So it's going to be about 8.5 atmospheres. And then ammonia is going to be 2 times this number, so it's going to be about 61 atmospheres. And again, we got some rounding issues, so as long as your numbers are close, you're going to be fine. So my Kp for this reaction is going to be the pressure of my ammonia to the power of 2 over the pressure of nitrogen times the pressure of hydrogen to the power of 3. Okay, so that's going to be 61 squared on the top, and that's going to be 169.5 and 8.5 cubed. So that Kp value comes out to be 0.0357 when you do the math. So what does that tell us about this equilibrium? Well, because it is less than 1, we could say the reactants are favored in this particular equilibrium. So the Kp-Kc kind of idea for relationship to 1 is going to be the same.